Greetings, here is MJ20, paper 41, question 8. Define the Tesla. Now, what is a Tesla? It's not a company, although the company is named after it. But here is a unit of B. You know how Newton's is the unit of force? So Tesla is a unit of magnetic flux density. Now, if you ever forget, just remember the equation F equals to BIL sine theta and rearrange such that B equals to FIL sine theta. But we need to simplify some things, so we're going to say theta is 90 degrees, and that's the angle between B and I. So how to define a Tesla? You can say it is the magnetic flux density of the B, which, when acting normally on a current, so acting normally on wire with current, the normally basically means the 90 degrees. So this means normal. Or in other words, perpendicular. Okay, so B and I, something like that. So that's gone. So acting normally on a wire with current, then that causes a force per unit length on the wire. So force per unit length is, the unit Newton meter on wire. Okay, so that's kind of like a short form version of this. Where do the marks come from? The very first one is the idea that B and I is perpendicular. So we talk about B, which is acting normally on a wire. So normal, I is normal to B. So this is first mark. Second one is, so when you talk about force per unit length on the wire, so that is this idea. And the third one, I didn't write it down, but we look at this, B, F, I, L. Usually we will say, okay, if you want 1 Tesla, then 1 amps. That's how we define it. But here they didn't say 1 Tesla. They just say Tesla. So we don't know if it's 1 amp or not. Well, we just say causes a force per unit length on wire. And you can say this like per unit ampere. Or just say per ampere lah. Okay, easier. Per ampere. How do we know that? Force per unit length. Also, don't forget ampere, because they didn't define 1 Tesla. They didn't say 1 Tesla, then you don't know whether it's 1 ampere or not. It's just per ampere. However many amperes there are. So that's based on this equation right here. So that's 3 marks, B1, 2, 3 here. Okay. Now, next, we come to this. Oh my. This this magnet looks familiar, but what is that wire sticking out of it? That's new. It's just a way of shaping it. So a slight tweak to the experiment looks like this. So you have a rigid copper wire carrying a current balance. It's balanced on a pivot. This is a pivot point. So it's like a seesaw, a child can sit here, seesaw, another child can sit here, and it can tilt either way. Only one part is between the poles of the magnet. So that means only the part that is inside here will experience the magnetic force. We can assume that, all right? So the wire is balanced horizontally by means of a small weight. So if a hanging, I don't know what to put there, weight. So this one means there will be a force acting on this wire beam, mg lah, weight. But also there will be a magnetic force acting on this side. And depending on how they're positioned and how the forces are like, the wire can tip, but you want them to be balanced, right? Okay, so we're going to see what's the experiment they want us to do here. So the wire is balanced horizontally by means of a small weight. So balance, so that means the moment, clockwise, anti-clockwise, is the same. Let me draw that out for you. Like this is the wire, right? You have a pivot point somewhere here. You have a weight causing a clockwise moment or torque, and you also have a magnetic force causing an anti-clockwise moment or torque. Okay, let's see the question now. This is interesting. They combine the AS topic with A2. Number 1, explain why the section QL gives rise to moment about the pivot. Why QL will cause a moment? So first you need to see, is there a force acting on QL? If yes, how is that related to moment? So remember, oh, moment or torque equals to force times distance to pivot. Oh, must remember your AS. So how do you, let's go and see what QL is. Where is QL? Okay, let's look at this one first. So here you have a force because of the magnetic field pointing from the left to the right. That's the direction of magnetic field. Current, did they say which direction is the current? God, they didn't exactly say, but they did draw something here in this diagram. Look very carefully. The arrows. Oh, they didn't label these, huh? So you gotta be alert. Current is flowing in this direction, means it's going down, QL, and then up. So if you want to look at just the QL part, current is flowing this side. So if you use your Fleming's left hand rule, take out the left hand, and you try to figure out which side is the force, I can say the force is pointing downwards. If you're not sure how to find downwards, redraw the side view or front view as if your eye is, looking this way. So you will see this magnet here, north, south, magnetic field pointing this way. Current going into the page. So the current will be going away from your eye if this is your eye down here. So that will be into the page, X. So the B will be your pointing finger. You point to this side, to the right side. So then you will say, oh, this is the forefinger. Point that way. Current middle finger. So you stick your middle finger into the screen or into your paper. And that will give you a thumb that points downwards. This is force, which is your thumb. Okay, so if you forget which is which, take a marker, draw on your hand. So force is downwards and acting on QL. So if there's a force downwards, then if you look at the whole picture, especially this one, the simplified version, if there's a force here, then there will be a moment because of this force, an anti-clockwise moment. In fact, let's change the colors. So this force is going to cause this moment. And why? Because it is a distance away from the pivot. So I don't know, D lah. So if you have a distance, you have a force, then you have a moment. So talk about both. So number one, you say the current in the wire, you must explain a little bit. Current in wire is perpendicular to the field. I just draw a perpendicular logo because I don't want to write the whole sentence. And because of that, it causes a force or vertical force. If you want to specify the direction, sure, go ahead. Vertical force downwards. Okay, so we talk about the force. So for moment, you must have force, but you also must have a certain distance between the pivot and where the force acts. So let's talk about that. And you say this force acts at a distance from the pivot. That's why we got moment from pivot, causing an anti-clockwise moment. There we go. If you find it like, wow, why so many words? You go and check the old drawing, right? So you're going to try to explain why is there a moment. So you must say, is there a force? Where the force come from? Is there a distance between pivot and the force? If there is, okay, very good. Can. So there is 2 marks here, 3 marks. One is you talk about current perpendicular to field. Here's one. And what does that cause? Vertical force downwards. Oh, got vertical force downwards. Downwards force. Okay, is the force at a distance? If it is, yes. The forces are at a distance from a point. So okay, can. You see the masking, they will say the force is not on the pivot. Actually, why on the pivot cannot leh? Because you think of it this way, your bar is like this. If your magnetic force is acting exactly on the pivot, will it cause a moment or not? Cannot, because that moment will be the force times 0 distance from the pivot. So that's what it means lah, okay? Perpendicular distance from the pivot, which is this one. So here is your magnetic force. Okay. Part 2. Sections PQ and LM do not affect the equilibrium of the wire. Explain why. Wow. So the answer is they do not affect. Now you need to say why. Why PQ and LM doesn't affect the equilibrium whether the wire will tilt or not. So let's go back to the diagram once again. We look very carefully at this thing. PQ and LM is at the side. What is the direction of the force acting on PQ and LM? What's the directions of the setup there? So if I want to redraw section PQ, I'm going to do it on the left side here now. Draw the side view. N, S. Currents here is going to be flowing down. So I can draw something like this. This is current. And the magnetic field is pointing to the right. So where will the thumb be pointing? The force. So this way you can do this. Your hand points to the right, middle finger down. Your thumb should be pointing out of the page. So I put here, out the page, and that is the force. Your thumb. Oh, so that means this section will experience a force this way, to the side. I try to draw it like pulling it apart like that. How about the other section, LM? So this is for PQ. Okay, on this side. LM is behind there. So let's redraw again. Okay, the hope is eventually if you do this often enough, you don't have to keep redrawing in 2D. But for now, since we just started, okay redraw everything. So magnetic field still from north to south, but now your current is going upwards because down, left, up. Okay, so upwards that way. So that will be like this. Current. This is for sections L to M. So use your right Fleming's left hand rule. Point your forefinger to the right, your middle finger up, and twist your arm a little bit. The thumb will be pointing into the page. So this into. In other words, the force acting on the wire section LM is the opposite direction that side. Wow! So how do we explain that it doesn't affect equilibrium at all? If you look at our diagram, we redraw this. Hello. The force here is either out of the page or into the page, and they cancel each other out. So it doesn't really affect the equilibrium. They are the equal magnitude, but they're pointing in opposite directions. This is like a throwback to the two-wire experiment. Remember, in the earlier, we will look at it actually in the next one. So just keep this in mind. Equal magnitude, opposite direction. Oh, okay. So how do we describe that? Yes, there's forces, but they don't affect equilibrium because they cancel each other out. So let's talk about that. So the forces, firstly, are horizontal. That's number one. But also they cancel each other out. So they're horizontal, equal in magnitude, and opposite in direction. So they really don't affect anything else because they cancel each other out. Opposite in directions. Or actually, and in opposite direction. Sorry about that. Okay, so 2 marks here. One, if you say they're horizontal. And not only they're horizontal, they're equal in magnitude, opposite direction. So this is the Newton's third law. Okay, so 2 marks for explaining why those two sections don't affect the equilibrium of the wire at all. Isn't it strange? Okay, this one is the vertical one. Oh, vertical. So yes, it will affect it's the only force that's pointing downwards, so it will affect the equilibrium of the whole wire. But the other two, you point here, I point there, cancel each other out. Okay lah, no need to worry about it. Alright, so that's the explaining part. Now we go to a calculation section. Section QL. We are zooming in on QL now. Where is QL again? QL is a section inside the magnetic field, okay. The part where we experience a force. Section QL has 0.85. I will call that the L. The length of wire inside the magnetic field. The perpendicular distance of QL from the pivot is 5.6. Oh my, let's draw the whole wire setup again. So the side view looks something like this. Pivot is right here. Distance here is 5.6 cm. Okay. And you have another mass hanging there lah. This is the weight. And here is your magnetic force. What color shall I use? Purple lah. So I'm going to change weight to be another color so we don't confuse ourselves. B. Green. Okay. Now you change something. Dun 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 dun. Well, current in the wire is changed by 1.2 amps. Oh my goodness. So what's going to happen to the force? It could get stronger, it could get weaker. We don't know. Okay. So maybe it is increased by 1.2. Maybe it's a decrease by 1.2. Who cares? But what we do know is that W have to move a distance of 2.6 either to the right or to the left. Whichever one. Okay, there's a change. So I'll call this the change in distance lah. To restore equilibrium. The mass of W, this is the mass, 1.3 times 10 negative 4 kg. Wow, very light. Show that the change in moment of W about the pivot is that much. So remember we say your W will cause a clockwise moment, right? This W will pull so that this whole bar will turn if there's nothing else on the other side. So normally we say the clockwise moment is the force times distance, right? Okay, so anyway, we know it's clockwise already lah. But now we're talking about change. So you can upgrade this formula a bit to say torque equals to F2D2 minus F1D1. Or you can just simplify this and say, since the force is the same, change in the moment will be the force, which is the same, times a change in distance. Okay, I don't know positive or negative. Never mind, change in distance. So here you can find the change in moment. So the force will be W times D. But let's sub in all the values straight away because not enough space now. So the force here is 1.3 times 10. Oh, must remind you, this is M, right? So I have to mg delta D. Okay lah, I write. So 1.3 times 10 negative 4 kg. Okay, that's in SI units. 9.81 meters per second. And the change in distance, which is 2.6 cm. So put centimeter. Okay lah, we already know it's meter. Alright. With that, we plug in our calculator, press. You should get a value of about 3.32 times 10 negative 5. And that is roughly about the moments that we will see that's change when you suddenly change the current. Okay, so when you change the current, then your W move a bit now, then you have to different moment happening here. So this is 2 marks. 1 mark comes from you knowing this equation, like this one, sub in. And the other mark is your substitution of correct values inside here. Final answer, no mark, because they already gave you the final answer. If you got stuck here during an exam, just skip this question, use the value they gave and continue on, if you can. Like write some numbers, whatever that is. Last part. Use the information to determine the magnetic flux density between the poles of the magnet. Wow. You kind of have to think a little bit. If this is your first time doing this, pause the video and try to brain this question properly. Maybe try out some ideas and see if it works or not. Then come back and we go through these steps together. So whenever you have wire balance like this, got the torque here, got the torque there, moment this way, we gotta go back to our basics from AS. What does it mean to be in equilibrium? So once some forces are changed, you need to restore equilibrium. And what does equilibrium mean? Think back to your AS. Equilibrium means no net force. Yeah, that's one. But also no net torque. In this case, we want to focus more on no net torque acting on this wire. So once again, the wire, the pivot, and the two forces. One, and magnetic force. So here you want to have a clockwise moment equals to the anti-clockwise net moment. All the forces clockwise plus equals to anti-clockwise. So the clockwise change in moment. Oh, we have to use change in moment. Should be the same. Clockwise change in moment should be equal to anti-clockwise change in moment if you want to restore or maintain equilibrium. So clockwise change in moment you already found. That is the previous 3.32 up here. Okay. W is causing a clockwise moment, but there is a clockwise change in moment, so let's write that down. First one is 3.32 times 10 negative 5. What is the force that causes the anti-clockwise moment? Or there will be a change in anti-clockwise moment. That will be the magnetic force. So you say, oh, FB times a certain distance, D. Can? Okay, so FB, we say D for now lah. It's given to us, which is 5.6 cm. So let's expand this a little bit. We want to find magnetic flux density B, right? Then we plug in here, F equals to BIL times D. But what is changed? Current was changed. So here is the delta. That causes a change in torque anti-clockwise. Now we are ready to do our calculation. Okay, last step, plug in everything you know to find B. So here I'll just write it one more time. Why do I write this so many times? Equals to B, I don't know what that is. Current increased by a certain value, 1.2 amps right there. So 1.2 amps, I'm going to write that down. That's a change in current. Length of the wire inside the magnetic field, that would be QL, so 0.85 cm. So here we go, 0.85 centi, don't forget. And lastly, distance. This one. So we put down there 5.6 times 10 to the negative 2 meters. Rearrange and finally you get B. Oh my goodness, 0.05812 is what I got. But for the final answer, I'm just going to write 0.058 because 2SF is pretty satisfying at this question. 3 marks for this. First one, of course, final answer. Second one is if you kind of know how to do this, that the moment is related to force times distance, but also force is BIL. So this will be a C1 for your equation. And also a C1 for substitution. All the correct values plug in. That's it. Okay, so this one, first time you do it, you will feel like, oh my goodness, my brain is going to split. But no worries, do it more. You'll see a lot of this to practice on in the next few examples and as well as for your own revision in past year questions. So that is all for this question. A nice torque moment balance kind of question, but based on the same principle as a current balance because you're still running current through a wire between the north and the south pole of a magnet. Okay, so that's all for this video. I hope that was helpful. I will see you in the next video.